Okay, so today we will continue the discussion on groups. So we will talk about some more definitions. So describe what is meant by abelian group, and then what is meant by finite group. And then we will talk about what is a subgroup. And then we will talk about the concept called cosets. And then we will talk about the last thing. This is the Lagrange theorem. Okay, so these are the things that we will cover in the first hour, and then after that we will talk about something new. By the way, we have just released the homework 5, so if you have time, please take a look. And then for the exam, so exam will cover only number theory. So the group things that we are talking about these days is just for fun. Okay, okay, and then yeah, but the assignment is quite hard. Yeah, try your best. Okay, so the due date is next Thursday. And then we will have our exam next Tuesday. Is that okay? Good, okay. Okay, so yeah, let's recall what is a group. Okay, so what is a group? So a group has a few things. Okay, so first of all, it has a certain set. There is a set, let's call it A, and then there is a binary operator, star. Okay, and then this star is closed. So it is a closed operation, which means that if you have two elements from A star A will still be some element in A. Is that okay? And then we need star to be not just closed, but it is also associative. So you have A star B and then star C, it is the same as you do the B star C first, and then you get this one, and then you have A star of the result. So associative. And then you for every, so there is an identity element. So some identity element E in A, and then it is unique. And then one more thing, for each A in A, there exists an unique inverse. Let's call it A inverse, such that A times A inverse is the same as A inverse times A, which is the same as B. Is that okay? So this is a group. Now, so what are some? So let's do some example of groups. So what are the groups that we have? So, for instance, suppose that, let's talk about the numbers. Let's talk about the numbers. Let's talk about the number 0, 1, 2 as a number, and then let's say the operator is this operator, 3. So what does that mean? This is the operator, which means that I add two numbers, but I take the remainder after dividing by 3, modulo 3 operation. Okay? So 1 plus 2, you get 0. 0 plus 1, you get 1. Is that okay? So in that case, actually this is a group. So first of all, this operator is closed. You get any two numbers here. After the operation, it's getting back into the set 0 and 2. Is that okay? And then it is associative. Okay? So you have 3 numbers. When you add them together and take a remainder, there is no difference in adding which 2 first. Okay? It is also there's an identity. So which one is an identity? 0, right? When you get 0, it doesn't matter. And then each one has an inverse. 0 has an inverse 0, 1 has an inverse 2, 2 has an inverse 1. Is that okay? So this is a group. Okay. This group is also special. Okay. This group is, if you take two elements A and B, so let's say I have this operation. So this is A plus B and then modulo 3. It is the same as B plus A modulo 3, right? So in that case, we call this group commutative. So this is going to be a commutative group. But we also have a name. We also call it an abelian group. So abelian group just means a commutative group. So abelian comes from this mathematician Abel. Okay, Abel is a mathematician from, I forget. It's like so the Northern Europe. I forget which one. Either Norway or Finland or Sweden. One of them. So Abel is a very famous mathematician, but he died very young. Okay. So this is an abelian group. Okay. So let's see another example. So how about this one? So let's say we have 0 degree, 120 degree, and 240 degrees. And then let's say we have the operation rotation by, yeah, it's just, let's, so let's say we have an operation star, which stands for successive rotation, one after the other. Okay, going to turn right. Okay, so this 0 means that I start at a certain location, I turn 0 degrees to the rightward, counterclockwise. 120, so I start at the location, I turn 120 degrees, something like this. Is that okay? Is that okay? 240 means I start at a certain location, I go around a circle by 240 degrees. Is that okay? Clockwise. Okay, so if I have 0 degree and then a star 240 degrees, which means that I do a 0 degree rotation and then a 240 degree rotation. Is that okay? Is that okay? So if you look at this, this is also a group. This is also a group. So first of all, the operation is closed. So if you do 0 and 120, you get 120. So it is there. If you do 0, 240, you get 240. You get 120, 120, you get 240, right? You get 120, 240, you get 0. Is that okay? You get 120, 0, and then 120. You do the checking for all the possible cases. 9 cases. Is it? 9 cases. So 240, 0, you get 240. 240, 120, you get 0. 240, 240, you get 120, right? Something like this, right? So no matter what you do, any operation on any two elements will still be in the same set, 0, 120, 240. So it is a closed operation. And this is also an associative operation because rotation is like you do the rotation this one, and then this one, you can do this two first and then do this last. Is that okay? And then there is a unique identity, and then each one will have an inverse. Okay? So 0 inverse 0, 120 inverse 240, 240 inverse 120. Is that okay? So this is actually these two groups are nearly the same, isomorphic. They have the same structure. So you can map this to this one, this one to this one, this one to this one. Is that okay? So these two groups are actually isomorphic. The same structure as this one. And again, we can check that this is also abelian. Okay? Now, but not all groups are abelian. So some groups are not. So for instance, so let's try for this one. Okay, so let's say have a group of all the 2 by 2 matrices. Can you see that? Let me get it back up. So let's consider, maybe I'll give it a special location. Let's consider all the matrix of the form 2 by 2. So all the 2 by 2 matrix. Is that okay? And then let's say we have the normal plus operation on the 2 by 2 matrix. What? Oh, okay, sorry. This is also Abelian. Okay. So for this one, this is also a group. Okay, this is also a group. Yeah, you can check that easily. It follows close operation, 2 by 2 matrix, add 2 by 2 matrix is still 2 by 2, right? And then associative, there is an identity element, 0, 0, 0, 0, the 0 matrix. And then each one has an inverse, right? When you have a matrix A, B, C, D, you have a matrix minus A, minus B, minus C, minus D. Okay? How about this one? So, how about this one? Is it a group or not? Is it a group? So let's say we have 2 by 2 matrix, right? Okay, you multiply them together, so you get a 2 by 2. So it is closed. Is it associative? So you have 2 by 2 matrix A, 2 by 2 matrix B, 2 by 2 matrix C. I have AB multiplied with C. Is it the same as A multiplied with BC? Yes, this is yes. So far, so good. Associative. Is there an identity? Well, yes. I have the identity matrix 1, 1, 0, 0. Is it? The I, the matrix I. But now there's a problem. Not everyone has an inverse. Okay? Not everyone has an inverse. So if you have a matrix like what? Like the opposite, 0, 0, 1, 1. Well, I don't know. Does it have an inverse? Maybe yes. But how about this one? This one, it doesn't have an inverse. Okay? Because the determinant of this matrix is 0. So it is not invertible. So in that case, this is not a group. This is not a group. Okay? So this is not a group. So this is not a group. Okay, but let's do some modification. Let's consider only invertible matrices. Invertible matrices of size 2 by 2. So this is, you consider all the matrices 2 by 2 matrix, and then this is a multiplication operation. Okay? Now, let's revisit again. Let's see if this is going to be a group. So each matrix that we consider, there exists an inverse. The determinant is not equal to 0. Okay? So first of all, closed. Right? If it is invertible, you multiply with an invertible matrix, then you get a 2 by 2 matrix, and it should also be invertible. Is that okay? Like this. So suppose that A is an invertible matrix, B is an invertible matrix, then AB should be invertible. The reason is that A is invertible, so there exists A inverse such that A times A inverse is equal to I. Is that okay? Now B is invertible, so there exists B inverse such that B times B inverse is equal to I, right? Right? Or, okay, then if you look at this matrix A times B, if we try to multiply with something like B inverse A inverse, it is going to be equal to I. Am I correct? Because matrix multiplication is associative. So A, B, B inverse, A inverse, like B, B inverse, you get I. And then you get A inverse, you get I. Is that okay? So you will see that A times B, this is a product matrix, has a inverse, which is like B inverse times A inverse, which is another 2 by 2 matrix, such that multiplying this one to this one, you get I. You get to the identity. Is that okay? Is that okay? So that means what? That means if you have an invertible matrix multiplied with another invertible matrix, so the result will also be invertible because there is an inverse. Okay? And then associative, and then there is an identity. The identity is I, and I is also invertible. Is that okay? Because I times I is equal to I. Okay? And then inverse exists, because by definition, invertible matrix means that the inverse exists. So in that case, this is a group. This one, it is a group. But this is a non-abelian group. Because in general, the matrix A times B is not equal to the matrix B times A. Is that okay? Okay. So some of the groups are abelian and some of the groups are non-abelian. If you are okay with this, could you please raise your hand? Okay, excellent. Next, so we are done with abelian. So this means commutative group. So we have abelian group, non-abelian group. And finite. Okay, so finite, we are going to talk about it. Finite is very simple. It just talk about how many elements are there. Is it a finite set or is it an infinite set? So in this case, this is a group, and the ground set here is finite. So this is a finite set, a finite group. Okay, this is also a finite group. This is not a group, and this is an infinite group because there are infinitely many number of matrices, 2 by 2 matrices. Is that okay? That's it. Okay. Okay. And if a group is finite, the size of the ground set A, we will call it the order of the group. So order means how many elements are there in that group. So the order of this group is 3. There are 3 items. The order of this group is 3. And then for this one, it is infinite. So the order is infinite. Or you may say the order doesn't exist. So it is not a finite number. Okay? So later, we will take a look of some special property about the order of the group. Okay? Okay? And next, we will introduce a new concept called subgroup. Okay. So it is like the idea of set and subset. Okay. Subset means that I take out some of the items and then I have a remaining thing. Groups and subgroup is similar. Okay. So the definition is this one. So suppose that suppose that we have a group A star. So A star is a group. And then we have a certain set B, which is a subset of A. Is that okay? Now, if B star is also a group, then we call B star is a subgroup of A star. Is that okay? So subgroup means that subset and a group. Okay, if you start with certain group A star, and then from the set A, I take out some elements so that I get B. So now B becomes a subset. But after taking out some elements, B and star together may not be a group because it may not be closed, or it may not be having an identity element, or it may not have an inverse for every element. Is that okay? Then in that case, So B star, we don't know in general what happens. But if B star turns out to be also a group, it satisfies all the group properties, then we call B star a subgroup. Is that okay? If you're okay with this, could you please raise your hand? Okay. So let's see some example. Okay. Okay, so for instance, so let me use example here. Let me use the example here. So for instance, okay. So this is a group, right? So integers and the plus operation is a group. Okay. So let's try E and plus. So E means even numbers. So this is going to be a group. If I have two even numbers, I add them together, I will get even. And then associative. And then it has an identity. 0 is there. 0 is an even number, it's there. And then what? And then inverse. So I have a number 5. No, 5 is not there. I have a number 10. Then I have minus 10. It is also even. Is that okay? So this is a subgroup. So this one is a subgroup of Z plus. Okay. But on the other hand, we can define E plus, then we can also define O plus. Okay. So let's say O is the set of odd numbers. So this is the set of odd numbers. Now then, this is not a group. Not a group. There are many reasons it is not a group. First of all, it is not closed. Adding two odd numbers, I will get an even number. It is not there. It is not there. And then also the identity is not there. There is no identity. 0 is not there, right? Okay, but it is still associative and it is still a unique inverse. But it is not a group. Okay? Is that okay? So it's not like we can take away anything that we want so that we still have the group property. To take out certain thing to get a group property is something special. So in that case, we will give it a special name. So it is called a subgroup. Okay? Good. Now, so we know, okay, so let's say A star is a group, and then now we have B star. Okay, and then we want to check if B star is a subgroup or not. So is B star a subgroup of A star? Then, of course, we can do the checking like to check whether the star is closed for B, whether the star is associative, whether there is an identity, and then whether there is an inverse. We need to carry off these 4 steps. But then, interestingly, okay, if the group is finite, let me see. But if the case that we want to check, but it becomes easy to check when the B is finite. It's a finite set. So how? Okay. So originally, we need to check 4 things. This is 1 thing, this is 2 things, the second thing, the third thing, and the 4th thing to check whether certain algebraic structure is a group. But if we know that B is a subset of A star is already a group, and B is finite, then we just need to check 1. We just need to check 1. We don't need to check associative. We don't need to check identity. We don't need to check inverse. Why? Okay, so this is why we are going to show. We just need to check whether it is closed.